I'm from Fraunhofer INT in Euskirchen. We perform also a lot of radiation tests, also in electronics. And today I'd like to speak a little bit about optics. We have a history, a very strong history in fiber optics, starting from the 1980s, where Henning Henschel built up a group here. So there will be a little emphasis on optical fibers, but Gonzalo asked me to try to cover the whole spectrum of optical materials a little bit. So I give an introduction to all the areas, or try to. To introduce just, I don't know how many people here are familiar with radiation effects on optics. Any hands? One? Okay. There are a lot of effects. I won't cover all the effects today because I focus on things that are relevant during testing, not during manufacturing for the radiation hardness. But what people mostly focus on is, or mostly know about, is the optical loss of optical power or induced attenuation of the materials due to radiation by color centers. But there may also be density changes, or stress relaxation, or changes in the polarizability of the materials. And it's interesting to know that all of the above can result in changes in the refractive index. So if you look for radiation-hard glasses that are optimized for optical loss, then and you're very dependent on the refractive index, then you might not have the best glass. Other effects, these are effects that are more affecting the passive parts of the glasses. Then there are active ones where there is light induced by different effects, fluorescence, luminescence, scintillation in some materials, or if you have particles faster than light, which is easily done for electrons, faster than light in the medium. Then you have Cherenkov light, which is a little bit like an ultrasonic boom you have mechanically for an airplane. For the particles, they induce a optical shock front irradiating in it. And then you can also have, if you induce a lot of charges, you can have a dielectric breakdown, because most or many of the optical materials are isolators, and these are also called Lichtenberg figures, where you can have these figures in there, which obviously reduce the optical capabilities of the glasses. So let me introduce, start with bulk optical materials. Usually here the testing is done basically the same as you test electronics. You do a strap stress test. You put your devices inside your radiation chamber, and then you put them out and do some optical measurements. Some labs have facilities to measure the induced absorption, but there are a lot of specialized optical capabilities, and some can only be measured in specialized labs that only do these measurements. And so there you have to think about how you're doing, bring your own setup, which is usually maybe not feasible because you have to make very sensitive measurements that need a setup that is fine-tuned in a lab to a specific temperature and so on. And the other alternative is you irradiate your samples in the irradiation facility and then have them sent back to you. If this needs more samples, because you need, for each step, you need samples that have to be sent back immediately. Otherwise, you might have large gaps of several days between the irradiation steps. And you have to think about annealing, because depending where you are, it may take some time for the sample, maybe up to a day to be there. You can cool them, for example, but that's not trivial too. To my knowledge, there's no dedicated standard for irradiating optics. There's an ISO standard, which is also referenced by the ECSS. That's the ISO 15856 about material irradiation. And this usually asks you to use protons, if you want to test for protons of 2 MeV to 200 MeV and electrons larger than 0.5 MeV. And the electrons can be substituted by cobalt-60, which has the advantage that if you use electrons, you induce charge. If you induce charge in the isolators, you may run, if you do go to higher fluences, you may run into the problems with the dielectric breakdown, which you do not have by cobalt-60 because it doesn't induce a net charge from the outside. And then a lot of glasses are anorganic components, but there are some transparent polymers. And if you go to polymers in materials, then you are also always sensitive to oxygen. And then you have to irradiate always in a vacuum, like we've seen in the talk before, or in an inert gas. So a typical test setup at our lab would be like this. This is our workhouse, our cobalt-60, large cobalt-60 source that can push a 22, if it's fully loaded, 22 terabecquerel or 600 curie cobalt-60 source in this tip, which is about a diameter of a bit less than a centimeter. And here you can put things around. This is very optimal, we see later for fiber testing, but you can put everything around. We put electronics down here, and here we can put samples. You always have to be careful to work cleanly, put on gloves, put on clean sheets in there, because irradiation facilities aren't always the optimal cleanest rooms, definitely no clean rooms. And here's an example of an typical test setup we use, where you can put the samples in here, and we use the light source coming from a fiber, which is widen the beam, passing through the sample, and then getting on an optical spectrum analyzer to get the transmission spectra. As an example, this wasn't done with this setup, but this is from a manufacturer, but it's a very nice description on radiation-hard glasses. This is a non-radiation-hardened glass. Once you go away from pure silica, glasses get very sensitive to the induced losses. And here you see 100 gray, 100 gray is 10 kilorats for the electronics guys. And here you have 8 mega gray, which is 800 megarats. And this is a hardened glass. Usually for bulk glasses, the way to go is to harden glasses is to induce cerium. And this here, this number gives the weight percentage of the cerium in there. And it hardens the glass significantly, but you always buy, everything comes to a cost, and you buy it with a reduced transmission window in the ultraviolet usually, which you can see. If you see the hardened glass is not as white as the non-hardened ones, this yellowish shimmer comes from the cerium addition. If you look into surfaces, then the ISO standards classify surface effects from 4 milligram per centimeter. And this is, if I calculated correctly, for silicon dioxide about 18 micrometers, about. So 10 to 20 micrometers. Below that, you have surface effects. Surface effects are relevant for things that are get in contact with very high fluxes of low energy particles, like in the radiation effects, if you're directly exposed to them. Usually these particles are stopped very quickly, so they are only relevant in the outermost layers. but there they may be very relevant because they can produce a very high dose. And the standard says that you should use protons with energies from 10 keV to 1 MeV or electrons from 10 to 500 keV. And this excludes cobalt-60 because the mean energy of the secondary electrons are usually a little bit higher. Yeah, and this is concerning from the optics part. This is usually if you have films on the outer layer of optics that can be directly exposed to space. If you plan the irradiation, you have to think about how thick is my layer and how far do I want to penetrate, and that determines your energy. This is a trim simulation with 50 keV protons, I'm sorry. This is a proton example here where you can go like 0.8 micrometers, something like that. And here on the right-hand side is a calculation from P-star from NIST, where you can see the energy and the range of the particles, and you see the 100 keV is about 1 micrometers. Here's 35 MeV, that is a typical energy we use for displacement testing at the nearby accelerator in the Jülich research facility we use for displacement image testing, and here you're to 1 centimeter, which is definitely too large. Just to give a little interesting example that we looked into in our lab, this is vertical aligned carbon nanotubes. You have a picture here on the right. This here is 2 micrometers, so it's about 10 micrometers long. Vertically aligned carbon tubes, and these can produce very low reflectivities, below 1%, and 0.9. 0.1% it should be. I'm sorry, very low, 1 order more. And typical black paint is much more. And so the functionality is usually dependent on the structural integrity of these nanotubes. So you are expecting a sensitivity to protons. We put them in the cobalt-60 facility, which is not what you should do for surface testing, but it was quick because we had them in-house, and we went up to 1.2 gigarad and showed no measurable effect, which wasn't quite expected. And then we went to low-energy protons at an implanter facility, and then you see after affluence of 10 to the 17, you have a significant increase in the reflection during the measurements. Okay, optical fibers. What are the difference to bulk glasses? Optical fibers are optimized for very, very, very low absorption to guide the light over very, very large distances, like kilometers, tens of kilometers, hundreds of kilometers. So small changes in the transmission may get significant. Examples are 100 millimeter optical fiber at 800 nanometers after 1 megarad. For a pure silica fiber, which you have pure optimized silicon dioxide, you have about 10% loss. And for phosphorus doped fiber, you have a loss, or you're down to 10 to the minus 200 milliwatts. So there's really large effect, which is also due for normal glasses, but here it's exaggerated because you have so much glass. Testing is usually done online, not in step stress, and it needs a highly stable equipment because during the measurement you see every disturbance. So usually you should irradiate it exclusive it and then not do any breaks or put something in and out of your facility during the irradiation of the optical fibers. Here's our facility again, the cobalt-60 facility with a fiber spool around it. So this point source is very good for all cylindrical or spherical symmetric objects. Here's our current setup where we use a white light source and 2 dedicated light sources at 2 wavelengths 1300 and 1500, which are typical communication wavelengths, which are switched. And then we can put two fibers in parallel. We have one reference channel which is put through down to the irradiation hall to get a very good reference on any disturbances. And then they are switched back and put on a spectrometer or on an optical power meter, depending which light source you use. And a typical result would be this for the dedicated light sources for 1300 and 1500, and also included bands with uncertainties for the measurement. And the right hand you see the spectrometric measurements up to this line. It's the irradiation, and then you have the annealing, which I didn't show here on the left hand side, which is in one graph here. This is wavelength in this direction and dose in this direction, and the color gives the induced loss. Then my colleague took some time to compare standards for fiber optic testing. There are 3 standards actually, which differ quite a while. I try to go to this fast because I'm late. There are sometimes different radiation sources used. There is often a dedicated irradiation time they give you, dose rate. They have very different annealing rates. And they also give you the fiber lengths before, which is a problem, because I mean irradiation time and dose rate depends on your dose, and this gives you only one dose here, and so it really depends what kind of doses do you want. If you're a high dose environment, you have to go to an accelerated test to high dose rates. This is a little bit short for annealing because you miss some effects. And the length is very dependent on the sensitivity of your fiber, because you don't want to have too large a difference of the light power inside the fiber. So you have to tune your lengths depending on, if you have a very radiation hard fiber, you might need 250 meters. If you have a very sensitive fiber, you're down to a few meters usually. What is room number in the standards? I put here are the different definitions of room number, including the ESCC, which is of course a standard for electronics, just for comparison. But I wouldn't ask this question if there weren't a problem with it, because these are wide ranges, like if you have a 10 degree range here, and we did some measurements of this exactly the same fibers with the same setup, with 29 degrees and 24 degrees. It's a 5 degree centigrade difference within this window, and it has about a 15% difference in the result. Then in fibers, an old effect that everybody knew and thought was not very important anymore is photo bleaching, where the induced light power during your test can anneal the fiber. And this is an old measurement from the 90s from Henschel, where he went brown. And keep in mind, this is decibels per kilometer, and this is in the logarithmic axis. And you have a large effect. Usually, people tell you that below 1 microwatt there's no effect, which was here. And it was thought that this effect was not as important anymore with newer fibers who got better quality. But the recent measurement in our lab shows that this still is a problem. And so you have to still be careful about the light power in your things. And then, 1 minute more. Then you have one last effect I want to discuss is bending radius. If you want to go to very high dose rates, you have to get very close to the source, and which means very small spools. And then you can see here for 4 centimeter spool with different fiber lengths, you can see very different effects in the radiation-induced attenuation. And I want to say two words about fiber Bragg ratings, which are interferometric structures you can put into fibers. They are temperature sensors, strain sensors, or used as mirrors for fibers because they reflect the light of a specific Wavelength. Also, depending on your manufacturing, there are large differences in the effect of radiation on the fiber, from very radiation hard to ones you can use as sensors. And here, this is the last slide, you also do the radiation online. And you think, since these are manufactured parts, you also might get statistical variations, like you have from part to part variations with electronics. But you can multiplex a lot of fibers due to gratings, due to their, if you put them in different wavelengths. And since they are temperature sensors, you have to be very careful to have them in a temperature stable environment during the irradiation, and correct for the small irradiations you always have. If you put the irradiation source in the room, you always will change the temperature a little bit because you include an energy source. Thank you.